Hey everybody, welcome to our next unit. This unit is called Thermochemistry, and basically what we're going to be looking at is how energy affects chemistry, measuring the changes in energy when chemistry happens. Now, this topic is very large. Lots of information is going to be coming at you over the next couple of weeks. So we decided to break it up into 3 smaller chunks, which we're going to call modules, as you can see here. The first one is called thermochemical equations, which is what we're going to begin today. Before we can get into the role energy plays in chemistry, we first need to kind of establish our understanding of what energy is. Energy is, in a very vague description, the ability to do work or cause change. But if you think about it, anytime we cause things to change, whether we're pushing or pulling or moving, what we're doing is we're expending energy. I like to think of energy as kind of like money or currency. It's the cost of doing things, especially in chemistry. Sometimes we pay money in order to do things in chemistry. We pay some energy in, or sometimes we get energy out. But energy is always either going in or coming out in a situation, whether it be in the physical world or in the chemical world. So energy can be a really difficult subject to kind of wrap your minds around because there's nothing tangible about it. We can see the effects that energy has on things and has on chemical reactions, but we can't really ever see or touch energy. It's just something that you have to kind of imagine. It's abstract. It's not easy to really wrap your minds around, but it's possible with a good imagination and lots of examples. So first, let's talk about how energy is measured. It is measured in a unit called the joule. That's capital J. And so when you abbreviate the unit for energy, you use the capital J for joule. In truth, a joule is not a lot of energy. It's the energy required to produce 1 watt for 1 second. Watts are a measure of power, and so joules are the energy to power for 1 second. Now, in truth, a joule is not a lot of energy. It's a very small amount of energy, in fact. To give you an idea, one single P has about 1,000 joules of energy in it. And so we don't really ever use individual joules when we're counting. Rather, we scale this up by using our metric conversions, and we typically talk about energy in kilojoules, which is 1,000 joules. Now, a little trick that food industry plays on you is that a calorie, which is the measure of energy in food, is actually not equal to a calorie, what you might think it is. 1 calorie is actually 4.18 joules. And if we already talked about how little joules really are, the food industry doesn't really want you to think about energy in terms of calories when you're talking about joules. Instead, they use capital C, or food calories. A capital calorie is actually 1,000 calories, little c. So in other words, a calorie in the food sense is kilocalorie. But imagine you're in the food industry and you actually are measuring the amount of energy in, say, a granola bar or something, and you look on the side of the label and you see 180,000 calories. Well, someone's going to be like, well, I'm not going to eat that granola bar. It's got way too much energy that I don't need. And so the food industry plays a little trick on you by measuring calories with a capital C, which is kind of deceiving, but now you know. A food calorie is actually 1,000 little calories, and 1 little calorie is 4.18 joules. When we talk about energy in science and in chemistry, we narrow them down into 2 broad categories. One broad category is energy of motion. We call that kinetic energy. And the other type of energy is energy that's stored. We call that potential energy. Now down here, I have many examples of different types of energy that we could encounter. And I want you to pause the video and circle all the ones in red that you think are kinetic energy, and circle all the ones in green that you think are examples of potential energy. And I'll do the same, and then we'll compare answers. So go ahead and pause the video now. Well, how'd you do? Well, let's take a look at each one of these. Obviously, something that's spinning is moving, so that's kinetic energy. But what about heat? Heat is also movement, right? You add heat to something, the particles are moving, so anything that's heat, that's moving. And it's not stored. Compressed spring, well, if it's compressed and being held in a compressed state, that's potential. Gasoline, that's kind of a tricky one, but the liquid itself is storing energy in its bonds, and that's really what we're going to be getting to here in the next couple slides, is how chemicals can store energy. Electricity is the movement of electrons, so that's kinetic energy. chemical bonds going along with gasoline are stored. Batteries sometimes is misconceived as a kinetic energy, but the actual battery itself is storing the electricity, waiting for it to be let out. And sunlight, sometimes students think is potential energy, but sunlight is the actual movement of the particles. The light itself is moving. After looking at these and thinking about it a little bit, maybe you have a little bit better understanding of what is moving and what is stored, but we're definitely going to dive deeper into these concepts. This was just kind of there to get you starting to think about this. In chemistry, when we focus on kinetic and potential energy, what we're really talking about is heat and the bonds. Heat is our example of kinetic energy, energy of movement as in heat. And so we know that the temperature is the measure of the average kinetic energy of the system. And so the temperature is directly related to how much energy is either being absorbed or released when chemistry happens. And that's going to be important here. We're going to talk more about that in a later video lesson. But the potential energy in chemistry is actually stored up in the bonds, as I talked about in the last slide. The gasoline, everybody knows gasoline goes into your car and you burn it in order to cause the car to move. Well, the burning is breaking the bonds and making new bonds, and overall the energy change causes the car to move and releases heat. That's the kinetic energy. But the potential was all stored in the bonds of the gasoline. And so yes, chemical bonds are little packages of stored energy. Sometimes the energy is absorbed, sometimes it's released, but when you think about an overall chemical reaction, you've got to think about the bonds that are being made and being broken and figuring out, does this reaction make more energy than it releases, or does it release more energy than it makes? That's the key behind chemical potential energy. We call this stored energy in bonds, bond energy. Pretty self-explanatory. We've been writing chemical reactions for a while now, but we haven't really talked about the energy that goes into or is released from a chemical reaction, even though we experience energy released and absorbed all the time when it comes to chemical reactions. We can probably think of a dozen examples of energy being released, like something starting on fire, combustion energy. That is energy, kinetic energy, that is released. But some chemical reaction actually take in energy in order for the reaction to go. We can use the chemical reaction to manipulate the amount of potential and kinetic energy in order to do work for us. That's the whole idea behind chemistry and chemical engineering is, can you harness the power of a chemical reaction to do work for you? And we're going to be talking about that work in the form of bond energy that's stored up and used maybe later. If you take a look at energy and the chemical and potential energy of a certain situation, when you add them together, it equals the total energy, which we call TE over here. It's the purple box. Well, the total energy of a situation doesn't ever change, but the potential and kinetic energy may change as long as TE stays the same. And so what we're talking about here is an inverse relationship. Like the kinetic energy can increase, but the potential energy has to decrease proportionally, because when they add together, they have to equal the total energy. Or maybe something is less kinetic and more potential, but either way, when you add them together, they should still equal the same amount of total energy when a situation happens in chemistry. And so what we're trying to establish here is that energy is always going to be conserved. There is no change. That's what we mean by does not change. Something may convert from kinetic to potential, but the amount of energy lost from the kinetic is the amount of energy gained in potential. And added together will always equal the total energy. This is what is known as the law of conservation of energy. We have a law of conservation of mass. We also have a law of conservation of energy. The law of conservation of energy says that in a chemical or physical process, the total energy cannot be created or destroyed. So mass does not convert into energy. That is a common misconception. People think you burn a piece of wood, now the wood turns to ashes. How did it get its energy? Well, they think, well, it lost its mass, it turned into energy. That is not true. The mass is conserved. We don't pay attention to the gases that are given off because they're invisible, and the ashes and the gases and everything that is produced in a chemical reaction is equal in mass to what we started with. And the energy does not turn into mass. Now, this is not true in a nuclear process, but in a chemical or physical process, these two things must remain true. So anytime we think energy is gained or lost, we really are just not tracking where it goes. Like we're not paying close attention where it came from and where it goes and how it's changing form. But in a chemical or physical process, whether it be a tree growing or burning a piece of wood or photosynthesis or anything that requires a chemical or physical process, energy must be conserved. And if you think it isn't, it's because you weren't paying close enough attention. Now I'm going to try and land the plane here in this last slide of this video lesson. How does chemistry relate to energy when we're really talking about chemical reactions? And as we know, the basis of chemistry is a chemical reaction. What a reaction does is it causes a shift in the kinetic and potential energy when the chemical bonds or the intermolecular forces rearrange. There's really two possible outcomes. Really, the one possible outcome is that there is more potential energy at the end of a chemical reaction and less kinetic energy, or the other situation is that there's more kinetic energy at the end of a reaction and less potential. Let's take, for example, this first one. If the bonds of the new compounds store more energy than the old ones, then what they are doing is they're stealing from the kinetic. So if your products store more energy than the reactants had in the first place, well then what you're doing is you're putting energy into the reaction in order to store more energy as products. And so these are related to each other. The kinetic energy has been converted to potential energy. Now, the other hand, if you've got bonds in the new compound that store less energy than the old ones, well then you're going to give it to the kinetic. So if you've got more energy stored in bonds on the reactant side than you do on the product side, well then what you're going to get is an excess amount of energy given out. And so that stored energy turns into heat energy, potential converts to kinetic, and in this case, energy is going to be released in the form of heat in a chemical reaction like this. So really what you need to do is pay close attention to the energy that's in the bonds. Is there more energy in the bonds as products, or is there more energy in bonds as reactants? And that's going to tell you whether or not a chemical reaction is going to release heat energy in the process of the reaction, or it might absorb energy in the process of the reaction. It's important not to forget about intermolecular forces here, because these could be applied as weak chemical bonds, and they work the same way in terms of storing and releasing energy. What if you've got a liquid which has high kinetic energy compared to a solid, and the liquid which has high kinetic energy converts to a solid? Well, in other words, the solid's intermolecular forces cause it to have more potential energy than it did to begin with. So essentially, when you cool something down and solidify it, you are causing a shift in the energy, less kinetic to more potential. Now you could simply melt it and it turns back to kinetic. So you take a piece of ice which has a lot of bonds, a lot of intermolecular forces, and melt it, and it becomes and turns into liquid water, which has more kinetic energy. Now in truth, more reactions end up releasing energy than absorbing energy, but there are plenty of examples of situations where energy is absorbed in the process of a chemical reaction. And we're going to talk more about those details at a future video lesson or in class in some notes. Well, that takes care of this video lesson. Thanks for watching.